So we have these limit properties, and we know how to evaluate simple limits of linear functions. What I want to do in this video is start to talk about how we can speed up the process of evaluating limits of more complex functions. So here in this example, I have the limit as x approaches 1 of 5x cubed minus x squared plus 2x minus 4. And in this case, this is a cubic function, right? My highest power is 3. This isn't a linear function. So I don't know if I can just take that number and plug it in. I have to kind of fall back on my limit laws here. So if I go back and look at my limit laws here, the first one says, you know what, hey, I can take this limit and I can distribute it over addition and subtraction using that sum and difference rule. I'm sort of skipping a few steps by distributing it more than once, but I think it is fairly intuitive that we should be able to do that. So here I would say, okay, I've got limit as x approaches 1 of 5x cubed minus limit as x approaches 1 of x squared plus limit as x approaches 1 of 2x minus limit as x approaches 1 of 4. And then I'd say, okay, well, this is better, but each one of these now still is not a linear function. Over here, this piece I could actually do, but I'm going to hold off on evaluating that just so that I can evaluate all of my limits at the same time. I look at this guy in particular, that 5, I worry about that constant multiple. But luckily we have one of our limit laws tells us, you know, you can take that constant multiple of a 5 and you can factor that out to the front. So I can think about this as 5 times limit x approaches 1 of x cubed minus limit as x approaches 1 of x squared. And you know what, since we're here, why don't we just go ahead and factor that 2 out. Limit as x approaches 1 of x minus limit as x approaches 1 of 4. We say, okay, well this is great, but these two in particular, right, this guy here and this guy here are still not linear functions. I still don't know how to evaluate them. But lucky for us, we had our power rule that said, you know what, you can carry that limit to the inside of the power and evaluate that inside part. So that's exactly what I'm going to do here. 5 times limit as x approaches 1 of x, this guy raised to the third power, minus limit as x approaches 1 of x. We're going to square that whole limit. And again, these two over here we don't really need to do anything with. Limit as x approaches 1 of x minus limit as x approaches 1 of 4. And now we're finally in a position we can say, okay, this guy here, x, that's a linear function. This guy here, x, that's a linear function. This guy, x here, this is a linear function. 4 over here, this is a linear function. You might classify it separately as a constant function, but in either case, we know how to deal with this. So we can just go ahead and take 1 and plug it in for x in each one of these cases. So I have 5 times 1 to the third minus 1 squared plus 2 times 1 minus 4. And then, okay, now we can go evaluate this. We should end up with 5 minus 1 plus 2 minus 4. 5 minus 1 would be 4, plus 2 is 6, minus 4, my limit is 2 here at the end. So a lot of work when we're dealing with polynomials. The other type of function we're going to see is rational functions. So, okay, now I have x squared minus 4x plus 1 over x plus 3. Again, I want to evaluate this using limit laws. Again, this is not a linear function, right? I've got a polynomial, I've got a quadratic here, I've got a, the denominator is a linear function. So, again, we're just going to think about how can we take this, how can we break it apart here. So, we had a quotient rule that said, you know what, you can just take the limit of the numerator and take the limit of the denominator. So that's where I'm going to start. Limit as x approaches 2 of x squared minus 4x plus 1 all over limit as x approaches 2 of x plus 3. Now my numerator, is not a linear function, so I can't deal with that quite yet. I would actually go ahead and take this limit here and distribute that to each term, just like we did in the last example. So the limit as x approaches 2 of x squared minus limit as x approaches 2 of 4x plus limit as x approaches 2 of 1, all divided by limit as x approaches 2 of x plus 3. I'm not going to do anything to the denominator since it's already a linear function. We know how to deal with that. So again, I look at this term right here, x squared. It's still a problem here, so I need to use my power rule here. Let's carry that limit to the inside of the power, so I'll have limit as x approaches 2 of x, this guy squared, minus here, if you wanted to factor the 4, you can factor that out. You don't necessarily have to. I don't think it's necessary. I think I'll just leave it here. Limit as x approaches 2 of 4x plus limit as x approaches 2 of 1 all over limit as x approaches 2 x plus 3. And now this is linear, this is linear, this is linear or constant, but again, in either case we know how to deal with it. X plus 3, that's linear. At this point we're good to go. We can go ahead and plug in x equals 2 in each one of these cases. So here I'd have 2 squared minus 4 times 2 plus 1, all divided by 2 plus 3. And then we're just evaluating this expression here. So let's see, I've got 4 minus 8 plus 1 all over 5, which would give me -4 plus 3, -3/5. So at this point we say, okay, when we've seen a couple of examples, we know how we could evaluate a polynomial and a rational function if we're trying to look at the limit of those two types of functions, but boy, it's just a pain. That was a lot of writing. There has to be a better way. Well, lucky for us, we have this handy theorem here. So this theorem says, assume that P and Q are polynomials and A is some constant. So this first one here works with polynomial functions. It says, if you're working with the limit as x approaches A of P of x, I can just take that number and plug it into my function and I'll get the same result. For rational functions, a rational function is just two polynomials being divided here. Again, the limit of a rational function, I can just take that number, plug it into my rational function over here, as long as the limit of the denominator is not 0. And again, that's just preventing us from dividing by 0. Like I said earlier, we're going to talk more about that case in the next section, which I believe is 2.4. So just really quick here, I'm going to prove this first one here for you, just because I think it's kind of an interesting proof, and it's relatively straightforward. It's easy enough to follow. I think it's a good proof to look at here. So I'm going to start off this proof, and I'm going to say how about we call our polynomial p of x. So if you look at a polynomial, you always have a constant multiple a sub n times x to some power, x to the n. And we're going to say we just have some arbitrary number, right? So the next one would be a sub n minus 1 times x to the n minus 1 power, right? So maybe this guy right here is x to the 4th, and this here is a factor of x cubed. And you'd keep going with that, blah, 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 however many terms that we have until we got to say, you know, a2x squared plus a1x plus a naught for our constant term here. If I wanted to look at the limit of these, if I wanted to look at the limit as x approaches, let's say, I used a, but I don't really like a. I'm going to use c here, of our polynomial function p of x. This is really saying, okay, the limit as x approaches c of all of these guys, right? You'd have a sub n x to the n plus, I'm not going to write out the rest because I'm lazy at this point. But essentially what we would do here is we're just going to kind of do what we did in that first example, in example 3. We're just going to apply our limit laws as we need to. So your first limit law you would apply it to, you would apply your sum and difference rule. So actually, you know what? I probably should have at least one more term. Let's go ahead and do that. A sub n minus 1, x to the n minus, n minus 1 plus blah, blah, blah. So you would say, okay, this is the same as saying limit as x approaches c of a sub n x to the n plus limit as x approaches c of a sub n minus 1 x to the n minus 1 plus blah, blah, blah. You'd have a bunch of different limits here, right? If I had 5 terms altogether, I'd have 5 different limits at this point. Next, I would take out these constant multiples and factor those out, just like we did in example 3. So here, limit as x approaches c, I forgot to factor it out. I would have a sub n times limit as x approaches c of x to the n power plus a sub n minus 1 limit x approaches c of x to the n minus 1 plus blah, blah. You do that all the way down the line, right? Every single constant multiple, just factor that out. All right, well, I still don't have linear terms, so okay, let's go ahead and carry each one of those limits inside of the power. So I would have a sub n times limit as x approaches c of x raised to the nth power plus a sub n minus 1 times limit as x approaches c of x, that whole thing raised to the n minus 1 power plus blah, blah, blah. Again, you would just do that down the line. Carry each one of those limits inside of the powers. And now we say this is linear, this is linear. I can go ahead and evaluate those limits. In each case, I'm just plugging c in for x. So I would have a sub n times c raised to the n power plus a sub n minus 1 times c raised to the n minus 1 power plus blah, 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 blah down the line. Eventually you'd get to, say, a 2c squared plus a 1c plus a naught. I didn't plan that out very well. But this is exactly the same thing as saying, you know what, just take that number and plug it into our function, p of c. So it's the same thing as if I had just taken c at the very beginning of my problem and plugged it into my function. And so that's what I wanted to show, which means that this is the end of my proof. So that's a pretty basic proof. You could actually do it for rational functions as well. That one would actually be even a little bit easier here because you could use the results of this one. For the rational function, you're just going to say, you know what, this limit, I can use my limit law to apply that limit to both the numerator and the denominator. And then after that, well, both of these are polynomials. We've already proved that here. So this one you could actually do a whole lot easier, but I'll leave that as an exercise to the reader if you want to try it out. But this gives us a really nice way to evaluate limits of more complex functions, which we'll look at some examples of this in the next video.